Okay, so now we have geometric sequences and series. This slide is just basically reviewing stuff that we've already talked about. So when you have a sequence, again, that just represents a list, and the nth term in that list can be represented as the first term times your common ratio r times n to the minus 1. When you're taking a partial sum, here n is 1. That's the sum of the first term. Your second sum would be s sub 1 plus s sub 2, and then you have your third partial sum, etc., etc. And we came up with this formula, though in general we tend to look at it this way, with a sub 1 factored out, 1 minus r to the n over 1 minus r. And we found that when we don't know what n is, we were able to substitute in and come up with this second. So this is when you don't know n, but you do know what the first term and you know what the last term is. Okay, something really cool happens when you take the sums and you let n go to infinity. In other words, when you're finding an infinite sum. So if we take that last series where we start off with 1/2, and then the next sum, when you added 1/4, you got 3/4. And if you plot all of these, so here would be like your x value, here's your y value. Notice you plot these, and because you keep adding numbers that get smaller and smaller and smaller, basically it gets, as these get really large, it's as if you're just adding 0, so you're not changing your sum at all. So what we say is this series is going to converge, and it only converges when you have a special case for your common ratio is less than 1, which is like saying it's between -1 and 1. And that's because when you multiply a fraction by itself, as the denominator gets larger, your whole value is going to get smaller. And lastly, we have a really cool sort of result of this geometric series, especially when it's infinite. You can take any repeating decimal and write it as a fraction. So remember that 0.99 repeating means 0.9999999, and it just keeps going, right? So I can write the first two decimal places as 99 over 100, the 2 zeros for the two decimals, plus 0.00, so now these would just add with the zeros, 99, so that has 4 decimal places, so 99 over 10,000, etc., etc. Realize that if you add that together, you get back to your original. So this is a geometric series where my common ratio, each term is getting multiplied by 1 over 100, the 2 zeros. My first term is 0.99, so I can find the sum, because you have 0.99 over, so 1 is the same thing as 100 over 100, so that gives me 99 over 100, which is 0.99 over 0.99, which is, in fact, 1. Pretty cool. So you've got that 0.99 actually equals 1. But you can do this on any repeating, it'll just have different sums. So if I take 0.36, so again, that means 0.36, 0.36, 0.36, that just keeps repeating. Now this is the way we did it, I believe, in Algebra 1. Since I have 2 repeating decimals, I multiply it by 100, so that gives me 36.363636, and I subtract this from my original x, which I let be 0.36, so that gives me 99x. These all cancel with these, and I just have 99x equals 36, which I can quickly write as 36 over 99. So in other words, 0.36 repeating equals that same number over 99. And then you can reduce. You can do this with any repeating decimal. Basically, you put as many 9s as there are repeating decimals. So here I have 0.125, so that's 3 repeating decimals. So I would write that as 125 over 999, and then you would reduce. Okay?